Please, step again. Start to restart or set. Release 86, go down next. Invite the speaker and ready.
We hit the recording here. Recording.
This is the
university and people will talk about understanding the photocatalytic what is on Strontium Titanate surface.
Okay, cool. All right, thank you very much. Good morning, everybody. I'm really glad to be talking about this work here. Doesn't have a whole lot of ferroelectricity in it, just a smidge, but one reason I think this is a really nice talk to be presenting at this particular conference is that I've always felt that this conference is one where theorists and experimentals really talk to each other and try to understand ways that we can kind of work on problems together. And this is a really good example of doing that, right? You'll see that a lot of what I'm going to present is actually theory that's been done by my collaborators, but you'll see there's a strong link between the experiments that we have and trying to understand exactly what they were implying about this process of photocatalytic water splitting on strontium titanate surfaces. We've been working on this for a while. Two of these students in there, Benjamin Biner and Amanda Lai, were my experimental students. Benjamin graduated in like 2015. So that gives you a little bit of an idea how long we've been working in this. All my papers take like 10 years. So that's kind of like where we're going. But I think you'll like what we have. We've been working with the theory groups of Maravi, Fernando Serra, and Cyrus Dreyer, both at Stony Brook. So it's a whole Stony Brook kind of enterprise to understand this process. So what is the process that I'm going to talk to you about? Water splitting on a photocatalytic surface. So the basics of what happens when you photocatalyze a reaction on a surface is you absorb some light and you produce a hole and electron pair. You have some charge separation and migration of those carriers to different active sites on the surface. And then in the case of water splitting, what you're going to hope to do is have these two redox reactions, or a redox reaction, oxidation and reduction reaction to generate hydrogen and oxygen. And so the obvious reason that we might want to do this is that we would like to make fuel and we would like to get the energy to do that from the sun, right? Because obviously that's what we're all interested in now. And we are going to have to solve our energy problems, have a lot of ways of getting energy and storing it. So if we can get a good catalytic process that's run by the sun to produce hydrogen, that becomes one of the viable ways to store and use energy. So the requirements for a material to do this reaction: the conductance band minimum of the material must be more negative than the reduction potential for the hydrogen, and the valence band maximum must be more positive than the oxidation potential. So you kind of have to straddle these two levels in this redox reaction, otherwise the reaction won't proceed. So there's this handy review that came out some time ago, and it kind of gave listed like where the potentials of various materials sit for this. And one of the things that's really nice is that some of our materials, for example, strontium titanate, sit in just the right position to do this reaction. The band gap's a little big, in a sense, because obviously what this means, because our materials have a band gap in the UV, is that we aren't really able to do this reaction with visible light. What would be nice is to have something where the band gap was a little bit smaller and it still straddled that those two potentials, but there's not a whole lot of materials that do that. So we're not going to worry about that. We're just going to do our reaction with UV and not arpeggiate into that detail. What we'd like to understand is a little bit how exactly this reaction works on strontium titanate surfaces. There are a number of papers on different kinds of materials that show that if you have crystals with different facets, you can have different kinds of reactivity on the different surfaces. So that's not surprising, right? When we talk about the surface being catalysis, we might already think that different surfaces might react differently. And that's what we're going to see in the case of strontium titanate, that the two different terminations, the strontium oxide and the titanium dioxide surface for the 001 surface, actually react quite differently in this reaction. And the punchline that I'll give away already is that you really need to have both of them for the reaction to proceed efficiently. Okay, so Here's our strontium titanate. There's two different surface terminations we can look at, strontium oxide and titanium dioxide. And we're looking which one of these two is the better suited for this oxidation to propose a possible mechanism for the oxygen production. So we know experimentally that it works in general. If you take strontium titanate and you put it under UV illumination, it'll be a pretty good photocatalyst. Oh, by the way, all this work has been published in this reference here, PRX Energy 1023002 2022. But okay, let me start showing you some of our results. So these are the first kind of things that came from my group in trying to do something interesting in the space of photocatalysis on strontium titanate. So it was kind of motivated by myself coming to Stony Brook University actually in 2008 and trying to get involved with some of the big activities happening there. We had a lot of people there and at Brookhaven who were interested in these photocatalyst problems. And I noticed, well, okay, these materials that I work with, the perovskite titanates, they are all photocatalysts for splitting water. So what can I do to add to this? And the first thing I thought, well, I have to have some way of knowing if a material that I produced, if I produce some sort of thin film, is doing what I want, is a good photocatalysis, right? So what would I do? Normally, if you're talking about a little film that's only got a 5 by 5 millimeter surface, measuring the hydrogen that's bubbling off isn't going to be a really effective approach, right? So that's not what we do. Instead, we use this proxy reaction, which is well known. I didn't invent it. There's a bunch of people doing this, right? Which is where you take silver nitrate, you put your sample in the silver nitrate, you expose it to UV, and you see where the silver is deposited. And normally, if you take a strontium titanate substrate that has been cut, polished in the normal way, and you do the reaction, you'll get little bits of silver all over the place. And that is the figure on the bottom, the left-hand side. On the left-hand side, the top one is what the surface looks like, topographic AFM. And then we look where the silver is, and it's just like all over the place, right? We then prepared some surfaces, and I'll say a little bit more about these surfaces and how we get them in a moment. But for now, I just want to show you these results. The middle surface, we've done some treatment where we started to remove some of the strontium oxide on the surface. So we start to get this step structure, and you'll start to see that the silver that's deposited starts to have some sort of ordering associated with it. It's not just random. We're actually getting more production in this case, but there's kind of like a pattern that aligns itself with the steps that are forming. And then we were trying to process this material to get the nice steps that you use to grow films on. We didn't really succeed in this particular case. We ended up getting these half unit cell steps. So what you'd have, and you can kind of see this in the profile on the bottom right-hand side, is you'd have this kind of lip where there was one material which is half a unit cell high, and then it would dip down to the other termination and then go up. So we've got both these terminations. And then the surprise was, when we did the reaction on this, the silver hardly deposited at all. So we broke it. Right? We broke strontium titanate. We did really well. No one wants to buy this stuff, but we had managed to break it. And as I tell my students, if you've managed to break it and you know how you broke it, maybe you could fix it. Doesn't always work, but that's the philosophy, right? So what we noticed here is that the places where the silver was depositing was on the edges, right? Either the step edges where you're dropping down 1.5 unit cells, or at these half unit cell steps. And we've kind of circled some of these. You can't see it very well here, but you can kind of see there's little bits there. So it's where the termination is changing is where you get silver deposited. So let me say a little bit more about the processing that we use to get these different surfaces. We're using a surface treatment, which is not necessarily the standard one. Normally when people are treating films, they want to get a titanium dioxide termination. They'll use a buffered HF process with annealing steps. We decided we wanted to try something a little bit different. We were using this process that my friend Andreas Rudiger had developed, where you would basically put the substrate in a digestion cell, right? It's a plastic cell that you put in the microwave oven, and it basically, you're doing a hydrothermal process where the pressure is quite high while you're processing this. And the water effectively attacks the strontium oxide and removes it. So it's one way to kind of remove your strontium oxide, and then you do annealing steps to try to get a pure surface. One of the things that kind of we found after really thinking about this a lot is that the end result of this, when we do our annealing steps properly, is not actually a titanium dioxide surface. What we find is that if you remove some of the strontium oxide, most of the large bits of strontium oxide, and then anneal this thing for a long time at high temperature, what actually happens is you get a lot of strontium oxide that comes up through from the substrate and then diffuses across the film. If you don't give it enough time to do that, that's when you get these half-unit cell steps on the edge, and they're actually strontium oxide. Right? If you give it enough time, you get a full strontium oxide surface. So the films that we're looking at are either partially like the titanium dioxide with a half-unit cell of strontium oxide arranged at the edge, or we can eventually, if we get the process right, get a fully strontium oxide surface. And then we can do those reactions on the films. This is just to emphasize the point that I was making, that this is what our films look like. You either have like a little lip of strontium oxide on the edge of a titanium dioxide terrace, or you have a fully strontium oxide surface. Oh, now I've gone there. Okay, so here, the set of results, they're not exactly the same results I showed you before, but they're consistent with that, right? You have your first one on the top left, you've got topography on the right, you've got before you do your silver deposition, and then on the right is when you've done it. You've done your silver. So the first one is similar to the first image we saw. It's just an untreated surface, cut, polished, right? And you get silver all over the place. Similarly, once we do a partial treatment, so we just treat this sample with the water treatment. We don't do any annealing, so we haven't reordered the material. You start to see some ordering in your strontium, in your silver that's on the surface. And then, of course, once you have this lip here with this strontium oxide, kind of like a ridge of strontium oxide here, you start to get these lines of the silver that are deposited, just like in the previous image, basically on either side of this transition, where you're going from strontium oxide to titanium dioxide. If you go to fully strontium oxide, the reaction essentially stops. There are a few bits where there might be some little bits of titanium and strontium left together on the surface, but by and large, you've killed the reaction. So we see that what's important experimentally in this system is to have both terminations, and it seems like for them to be close to each other, right? It's not good enough if they're like microns away from each other, right? In solution, you really need to have the two close to each other. And so we wanted to understand why that is. A couple of other observations. We did this experiment too on the supplied titanium dioxide terminated surfaces that we get from Crystech. They're treated in Twente with the standard buffered HF process, and we see a reduced amount of silver deposition. I think that what's happening here is because there's some residual fluorine left from that treatment, those acts as sites where the silver can deposit. What we found when we grew a strontium titanate film with a titanium dioxide surface, we again didn't get any deposition. So these pure surfaces that are either just strontium oxide or just titanium dioxide don't seem to have the reaction. Funny story, the reason that we did this water process was because I was worried I wasn't getting enough substrates from Crystech. At one point, they were really hard to get, and the word on the street was that Lane had bought them all. But yeah, so it was like we would only get a small allocation of these treated substrates. So I was like, okay, I need to invest in my own treatment procedure, which was the real motivation for doing this water treatment, not actually to do photocatalysis, but it was a happy accident. Anyway, the last experimental thing I'll show you is what happens if you introduce ferroelectricity. It's a conference on ferroelectrics. There should be at least one slide with something ferroelectric in it, right? If you do this on lead titanate, the reaction works. But what you find is that it's very sensitive to the polarization direction. So if you go and you write domains using your AFM tip and you look at them in PFM, if you have down polarization domains, you'll get silver deposited on them. And if you have up polarization domains, you won't get that. And what we found as well is if you put a strontium titanate surface on top of the lead titanate, you got something similar. It's not quite as dramatic as in the case of the pure lead titanate surface, but essentially what happens is all the stuff that I'm going to tell you about now about the importance of the different surfaces gets overridden by the polarization. If there's enough polarization in there, that will basically allow the reaction to either proceed or not. It'll kind of overrule these effects. Now, of course, you know, that suggests that maybe ferroelectrics might be good for this, but there's also good reasons why you might want to stick to just the pure strontium titanate. And you certainly don't want to be writing like PFM domains on every single photocatalyst you're going to be using to produce hydrogen. That seems very labor intensive. In any case, let me tell you some more about what's happening with strontium titanate. Why do we have this interesting reaction on the surface? Because that's our real goal. So the simulations that were performed by my collaborators, the questions we need to answer: what surfaces are responsible for each half reaction in this redox reaction? Is dissociation of the water on the surface important or necessary? Are the energy levels of the photooxidative species linked to the reaction sites? And really, bottom line is, what are the conditions that an ideal surface should satisfy to see photocatalysis on strontium titanate? So the computational methods, there's a number of computational approaches that were taken. One thing that was done here, there was basically some molecular ab initio molecular dynamics performed using Siesta, and basically they've taken a strontium titanate slab, and they've got molecules in the vicinity of these surfaces, and basically they run this and they see what happens in terms of where the water goes in the surface. Oops, there we go. Okay, so after they do this, they get both physiabsorbed water and associated OH minus on the two different surfaces. And what they see is that basically there is water absorbed onto this surface by this lone pair, and you get hydrogen bonds with the bulk water through this thing. So really there is this strong reaction between these surfaces and the water. And when we look at it in more detail, one of the questions we want to know is, where is this hole that we're getting going? So where's the potential trap? And you can basically assess this by looking at this hydrated surface. So we look where the OH minus and the strontium is, and we see that here is present at the top of the surface, and they're strongly localized, so these will act as good surface hole traps. On the other hand, the OH minus TI ones, which are these brown ones here, they're very delocalized, and they're less likely to facilitate an oxygen reaction. So based on this, it looks like the sites that would be most effective in facilitating this reaction, based on where the hole that's coming from this reaction will be, is the strontium oxide. Okay, was there a slide between there? No, I think that's what I want to do. Sorry, this is not quite responding at quite this speed that I want to. Okay, all right. So the other question that we had, so we were looking before, I showed you a picture where we showed what the alignment of the strontium titanate bands was for bulk strontium titanate in relation to these redox reactions. We'd actually like to know what it is like for our two different surfaces, right? And the way to do that, or the way the approach that was taken, was to basically try to find out how the energy levels would align within the strontium titanate water interface. And in order to do that, they followed this approach here that's in this paper, where they first find where the water 1B1 energy level aligns using a simulation of a water slab and vacuum. And so they find where this level lies. And then they do something similar with a system that is strontium titanate with water on either side, right? And so then what happens is, in order to get the alignment right, they shift this E1B1 level that comes in this simulation to match that one. And this gives you an idea about how the energy levels line up. So one thing to mention now in this simulation is we now essentially have a system that has both terminations in it, one on either side. So there's a strontium oxide on one side and a titanium dioxide on the other. So when you do that and you look at the relative alignments of these potentials, you see that the fully solvated strontium titanate hydrogen system would have the correct band alignment. By comparison, if you look at strontium oxide with the vacuum or titanium oxide, you'll see that strontium oxide, in terms of the energy levels, is much less isn't in the right place to drive this reaction. So the simulation that we have here that has these levels here is essentially a 50-50 system, right? You've got, on one side, you've got your strontium oxide and you've got your titanium dioxide on the other. And you might imagine as if you shift that balance towards strontium oxide, you might be moving this up and the reaction would stop happening. So this is I'm kind of prepping you for the idea that strontium oxide by itself isn't good enough to do the reaction. So then we wanted to look a little bit more at a mechanism for how this works. And the mechanism that was considered is this idea of a proton-coupled electron transfer. following this framework that's in this paper here. And essentially, what you have is a number of steps where in each step, a proton coupled with an electron is either removed from an OH minus species or from a water that's bonded to this OH minus. So I'll show you what this looks like here. Right, there are these 4 steps that are gone through, where here is the oxygen that we're dealing with, going from OH minus, goes to an oxygen minus radical, goes to an OOH minus, goes to O2 minus, and finally goes to OT. And O2, sorry, the oxygen molecule that we want to remove from this system, right? And in each of these steps, there's a transfer of a hole and an electron. Right, so this is basically what we're showing here. So when they calculated the energies on a strontium oxide surface, they see that the first step has a big activation energy. That's the rate limiting step, and then after this, there are these smaller activation energies. In fact, the second step doesn't require any more energy to proceed. There's also consideration that you might consider 2 electron processes that would combine these steps, and that's also a viable pathway forward for the strontium oxide surface. But what's interesting is when you look at the titanium dioxide surface, you get stuck after step 2. Step 3 never happens, right? So you can go through these, and then they never see any further steps, and they don't see this vital last step to conduct the reaction. So what you're seeing here is that although titanium dioxide might have the energy levels in the right place, the reaction can't proceed on that surface. You can get some insight by that by looking at the spin density of where the O minus species is here in strontium oxide. You've got this nice localized orbital that can react well with the water, whereas in the case of titanium dioxide, it's quite delocalized over this surface and less likely for this reaction to occur. So these are the conclusions then, right? You can't really do this with either pure SRO or pure titanium dioxide. That's certainly what our experiment showed. And it showed also that you needed to have these 2 terminations in close proximity to each other for the reaction to occur. So then we look at the band alignments. The band alignments look okay, right? And then the real clue as to why you need both surfaces is because when you can only get this process that we think is what allows this process to occur on the strontium oxide surface. So you really need the 2 things together, right? The titanium dioxide is vital because it puts your energy levels in the right place, but the strontium oxide is where the reaction is occurring. And they need to be in close proximity to each other. Exactly how close? Well, that's a great question. And it kind of gets into the idea of then, well, what is the extent of this electron hole pair that you've excited during the action? And so it's probably about the level of the exciton that occurs there. Anyway, that's basically the results I wanted to show you about. I think that they're very interesting. Of course, you might then say, well, how do I transfer this to something that's actually useful? Are we going to be wanting to do tiny little pieces of substrate of strontium titanate for our action? Probably not, right? We're probably going to be using some sort of powder or something like that. But if you think about it, the processes that we're developing could be quite transferable to that. They're essentially chemical processes in annealing and could easily be applied to something that isn't this pristine kind of thin film. The thin films are necessary to get the understanding, but there is a pathway, I believe, to eventually turning this into something that's hopefully useful and maybe will help us drive around in hydrogen cars. With that, I'd like to thank you for your attention and take any questions.
Thank you, Max, for a very interesting presentation. So open for discussion.
Shahal from University of Nebraska. I have a question. First one, if I substitute discuss something actually the list of the steps into the length scale methods?
Not in any systematic way, but naturally, I think it would matter as for example, it changes how this diffusion process of the strontium on top changes. So we did a little bit of work on that, right? And each time you change your miscut very much, like by a large amount, then you obviously have to change your processing. That's really one of the things that even we see that with the buffered HF, right? Like if the miscut is very different, you're going to need a different annealing time. You're going to need a different processing time. So all that is true for this technique as well. As far as like, could you get the steps close enough to really drive the reaction? That's an interesting idea, but not one we've explored.
A second question, I'm not quite follow. Show the Kelvin motion on scale. Is that a follow?
Oh no, it's so what it is it is actually lead titanate film about 20 nanometers thick, and then we put just 3 unit cells of strontium titanate on top. So that's where the ferroelectricity is coming on. It's a little bit like the superlattice approach, except instead of being a superlattice, it's just strontium titanate capping layer. And honestly, this is really like what originally motivated us to start doing this at all. I thought, well, I've got that capability, right? I can put ferroelectricity into things that wouldn't normally have ferroelectricity and see how that goes with the photocatalysis. And in the end, what we found is actually this problem just on strontium titanate was interesting enough to keep us occupied for quite a long time, right? But yeah, that's what that is. Yeah, it's not just strontium titanate.
Okay, but the strontium titanate, if you strand, it can be this column, right? So using the have some synergy between the correlation and the combination facilitated.
You could do that. That's not what we did. This is strontium titanate strained on strontium titanate, so it's not right. It's all on strontium titanate substrate. So this strontium titanate isn't strained enough. You could try that, but it would obviously be quite a different, yeah.
Yeah. Thank you.
Nice person to respond to accusation. Taking on some, actually very cool. So one comment, so in like solid state cells and analysis systems, strontium off segregation to the surface is really seen as a terrible thing.
Right.
Turns out. My question is, okay, so now I have strontium oxide on the surface. It's in water. It's like it was acidic as catalyst in water. Does the strontium oxide fall off, or does it hydrolyze? Turn into hydroxide, and we would have sustained reactions within that case.
Yeah, we never like went far enough down the road to see what would happen, right? Like if we left it for long enough, we'd eventually get the like massive amounts of silver on the surface. So we intentionally decided to look at that early stage because that's where we could see something interesting going on. There will be a limiting point, right? I mean, the water is reacting with the strontium and do that. Whether there could be some sort of refresh process is an interesting possibility. Yeah, what I should know more about, but I don't, is like, what is the state of the art? Are there people trying to use strontium titanate in a real application, and how good do they do there? I don't know the answer to that question.
Other questions?
How can we maximize? So, since it is a ferroelectrics context,
I mean, I was invited, man. So, to speak about this, so it's not my fault.